All right. So today we'll be talking about volumetric analysis. Now, when we talk about volumetric analysis, we are talking about some in its plain explanation or simpler words or relatable words, those experiments we do in the laboratory that has to do with the calculation of volumes, that make use of volumetric tools, things that would tell us the volume in liters, or tools that are rated or measured in liters, centimeters cube, meters cube, and so on. Okay, so there are different volumetric tools. Okay, so yourself, can you tell me anyone you can remember now that they use in the laboratory for volumetric analysis? Any volumetric tool that is used to measure the volume of liquids in the laboratory. If you check these particular tools, they are measured in volumes. They have standard markings. Yes, Melody.
Ma?
I said when we talk about volumetric analysis, we talk about analysis that makes use of volumetric tools. Volumetric tools are tools that um, are used to calculate volume or to measure volume. And you usually see that they are rated in centimeters cube or in liters, or that's their measurement, or in decimeters cube or whatever. Usually centimeters cube and liters. So can you tell us any tool like that you find in your laboratory at school? Mention some of those tools. Melody, you don't know any?
No, ma.
Really? Okay, can you now tell me of any tool you find in your laboratory?
Ma, is Buret among?
Yes. So how do you know with if that burette is among? Or did you just guess it? Now, how you will easily know, like I said, they are measured in volumes.
Ma, is Buret among?
Yes, it is. Like
Pipette.
yes, these things are measured in volumes. I hope you are not mentioning it because you can see it on the screen. Okay, so we have
I'm not even seeing
burette.
your screen.
Really? I'm sharing my screen. Can you see my screen?
No.
Ah, that means your network is probably not strong. Let me stop sharing and share again. Can you see it now?
No.
That means you can see nothing, that I'm sharing nothing.
Yes.
Who else is in the class? Okay. There's no learner in the class to for me to ask. But I can actually see it from my other device that my screen is actually sharing. And I'm about to draw something on the screen, so I don't know how you are going to see it. So can you see what I'm writing on the screen?
Maybe in the network.
Yeah.
Nope.
Okay, I'm actually trying to draw a pipette. Okay, pipette looks like this, the one we usually use in our schools. And a pipette, you would see a line close to it. What measurement is in that line? That line that when you have you done titration practical in school? Have you done titration before? Melody.
That's what I'm doing in my personal reading now.
Yeah, but I mean, have you done the practical at school before?
No, no, no.
Yeah. What class are you?
SS3.
And you've not what okay, what practical have you put now done in the laboratory? What chemistry practical have you done? Ah?
My school, we don't have a laboratory.
Oh, is it not um what's the name of the school that not Oba Kenzua, like Army Day? The one at um Uselu, something like that. Like it's close to Uniben,
No, no, I'm in Nicobar Hill.
Iboba Hill. But I think it's a big school. Why don't you have a laboratory? How are you not going to do your exam without the laboratory to carry out the practical, or even we maneuver it? Okay. So now that you can't see my screen, how do we do?
I'm seeing your screen now.
Okay. Now in titration practical, I would actually there are actual practical videos you can go and watch on YouTube. Are you hearing me? To see the
Yes,
process.
ma'am.
So I don't want to play a video in this class that you'll be watching. I don't want that. But I will explain the process to you. Okay. Now the essence of practical of titration, there are different titration. We have acid-based titration. The acid-based titration is base neutralizing an acid, okay, to give us salt. That is neutralization process. Okay, that's the most common one. And then we have another type of titration that is called redox titration, reduction and oxidation. Okay, so but let us talk about acid base titration. Now, there are different tools. There are different tools used in the laboratory for acid base titration process. Okay, first off, we have the burette. This is how the burette looks like. Let me show. Yes, this is a good setup, kind of. Now, the burette, if you look into this screen, this is the burette. This one I'm pointing out is the burette. It is being clamped. This thing I'm coloring red is the clamp. So you use the clamp to hold the burette onto this stand. Okay. Now this stand that is connecting the clamp to the burette is called a retort stand. Are you seeing it? This thing here is a retort stand. Okay. And then this one here is a pipette. a pipette. All right, and this thing here is called a conical flask. Please, can you mute your mic if you're not speaking, except you want to say something, please? Okay. So these are the basic tools, okay, we use in carrying out acid-base titration. Now, first of all, we want to do this kind of experiment. I said we have a retort stand. Don't mind my drawing. Let's say this is a retort stand. This is how it usually looks like. Okay. A retort stand. See the spelling. Retort stand. It stands there and it has usually a clamp attaching it. The clamp is what is going to hold our burette. This is our burette. Mhm. Please give me a second. Let me get an actual picture. And one thing about the titration experiment, in all the things we are doing, we are aiming towards two things. The first thing we are aiming towards is to find the concentration of an unknown, a solution of unknown concentration. That's the first thing we are aiming towards. The second thing we are aiming towards when we are actually doing the experiment, or the thing we are actually aiming towards when we are doing the experiment, is to get an equivalent point, to get, or what some will call end point, is that point where color changes. Okay, so that is our aim. Yes, I've gotten a picture. Please confirm that you can see my screen. Can you see my screen? Melody
Yes,
and
ma'am.
okay. Now if we see this setup, okay, this one is more clear. Even though that the first one is actually the one that is complete. I said this is the burette. Okay. Now in a titration reaction, okay, what happened? These are the volumetric tools I'm telling you about. That's why titration is a volumetric analysis. This burette is a volumetric tool, right? Why? Because it's measured in volume. All these lines we are seeing on the burette, okay, are measured in centimeters cube, or depending on. So at this top, there will be a point where it is zero, okay, maybe at this point. So when we are filling your burette, you will end at that initial point of zero. Okay, so let's say 0 centimeters cube. That is volume, right? So that's the burette. Not only burette, also this conical flask is another thing that adds measurement, and the measurement is also in volume. So there are different sizes of conical flasks depending on the one you're using for the titration. All of them have their overall volume. You can see a conical flask of 25 centimeters, 250 centimeters cube, or whatever the number is. Okay, So when you see all these marks, all these line mark, and you see the units is centimeters cube or liters, you know that that is a volumetric tool. Okay, retort stand a volumetric tool? No, because it doesn't measure volume. Okay, there's no measurement line on it. It's just a stand to hold the burette. Okay, and then pipette is another volumetric tool. This is the pipette, you must have seen it before. Now this is the pipette, this thin something at the middle here. Okay, this is our pipette, and the pipette at this point that is red, okay, you see it is usually 25 centimeters cube. Okay, so it is also a volumetric tool. Okay, so these all setup are the things that we need in um, carrying out our titration process. Now, there is what is called a titrant. Titrant. And there's what is called an analyte. Now, a titrant, okay, is the solution with known concentration. So is that solution that's in your practical question, they will tell you the concentration of it. Okay, so you know the concentration. They will tell you the concentration is so mole per liters. Okay, you know that's the unit for concentration. They'll tell you it's like mole per liters. They'll tell you maybe 0.1 or 5 points whatever. Okay, so the concentration is known. Now then the analyte is the chemical or the compound or the solution, the compound in the solution with unknown concentration. Now unknown, it's having unknown concentration. So how do you know which is which? The titrant is what you put in the burette usually. Okay, and when we are carrying out a titration experiment, it is this burette, okay, that is usually the base. Okay, and then the analyte is the one you put that you suck through the pipette. Okay, so for this particular pipette that I showed you is the one that we have to suck it. So not suck it like into you, like draw it rather with your mouth. So that's one you find in the that you take with the pipette into a conical flask. Conical flask. So what happens is, and it's usually the acid, what happens is that the first step is to set our retort stand and our burettes. So this is our retort stand. Okay, and this is our burette. So the first thing that we need to do is to set it up, and then we will measure our known concentration of base now. Okay, and we'll pour it into this burette on up until the marked parts, the part marked 0. Okay, that is, we'll now write it down and say, oh, this is our initial reading. It's advisable to start your initial reading from 0. So we'd say that is our initial reading, 0. So titration process, you carry it once, twice, 3 times. Okay, the first practice is called the rough reading. So you don't really include that in your calculations. You don't really consider that. That is just like a preamble process, something like that. Okay, and if your initial reading is 0, you should have also a column stating your final reading. What is the final reading all about? Is the reading that will be, no, let's take it one step at a time. So when you feel up your burette to the circle parts. Remember, at this bottom, there's a hole in the burette where the chemical can be rushing down from. Then you, as you have filled up your base in the burette, you go and you use your pipette. Okay, this is the pipette that's like you saw earlier. You use your pipette and measure usually 25 centimeters cube. Okay, you measure it of your acid. Let's say your acid is in this beaker, or like that is the analyte now. You you measure exactly 25. Accuracy is important in titration. Okay, so when you measure that 25 centimeters cube, you hold it just as we saw. Is we see they are holding it here. You see the person's hand at the top. As the person has take in the unknown concentration into the pipette and it has reached the mark point. Once it reached that mark point, you quickly hold it and then you pour it into our conical flask. This is the conical flask. That's what the person is doing here in this middle drawing. They have already sucked out the acid into the pipette and held it when it gets to that 25 mil and what milliliter, yeah, not centimeters cube, mil, and drop it into the um conical flask. So when you drop it into the conical flask, what is the next step? That conical flask that is now carrying the 25 mil of or centimeters cube of our pipette, sorry, of our analytes, which is the acid, you will now put the conical flask here. This is our conical flask. Now it is now the D time. The main thing is about to occur, which is the titration. So what do you do when titration is occurring? Like I told you people, Melody, you can go online, watch videos about it, okay? I don't want us to just flow with the video here. That's why I'm not sharing a video now. When we put when we put our flask beneath our base, remember this conical flask is containing an acid and this is containing a base. So this is where the neutralization reaction will now occur. From the clamp, these are burette will have something that we would be using to, will be opening so that our base will be flowing um into the conical flask. Okay, so you allow it to be going drop wise, drop wise, drop wise, until as you're doing it, you are shaking it. You are not removing it from that position where it is. In that same place where it is under the burette, you keep allowing it to be dropping into your acid and you keep shaking it until the color changes. Oh, please. Immediately you remove, when you get your acid in the conical flask, you also put in an indicator. We did indicator in the last class, right? There are different indicators. So, but one of the most common ones we use for this case is phenolphthalein. Phenolphthalein is colorless. Okay, so when we use phenolphthalein indicator, when we drop, only 2 drops is enough. They don't use to pack it. You put 2 drops in your acid and then you put it under your burette. When you put it under your burette, that's when you now be allowing your base to be dropping into your acid. Drop, drop, drop. As it's dropping, you're shaking it, you're shaking it, you're not removing it, you're shaking it until it will get to a point where you see a color change. It will now change to pink. Remember, that's the color change we observe when phenolphthalein changes in acidic condition. Okay, so it will change to pink. Every indicator have what they will change to. Okay, so remember that as the base is dropping into the acid, it is now reducing. So it is going from this 0 point to maybe 10, 20. So it reduces. So it will reduce to a point. That point where it reduces to, you will now take that number. That number will now be your final reading. Let us say it is 30. So that is to say the amount of base that was required for you to neutralize 25 ml of acid was 30, because 30 is the final, 0 is the initial, so 30 minus 0 is 30. So you require 30 ml of acid to of base to neutralize 25 of acid. So that is your rough reading. You repeat the process and you can fill back your base, get back another acid, you repeat the process again, and so that's how you keep repeating it for 3 times. So that's what titration process is about. Now the reason for all this, it helps you to get your volume of acid, okay, which will now help you to get your concentration of your unknown, which is the analyte. So this is actually a practical topic, it's not a talking topic. So we'll deal with the calculation aspects. Okay, like I said, you should watch videos on it. It will help you since you've not done the practical at all. So back to uh discussion. Please give me some seconds. Let me plug in my laptop. So far, do you understand all the thought, the explanation, please? Yes, I saw Winner joined. So Winner and Melody, do you understand? Golden, also Christine, do you understand?
Yes, ma'am.
Okay. So that is titration for you. Like I said, you might be asked maybe in your exam, it might be acid-base titration, it might be redox titration. Redox titration has its own process. So let's move on to calculations aspect, please. So these are some the materials that we use. White tile. The white tile is for us to be able to see the color change more reliably or better. Okay. You can see phenolphthalein colorless in acid, but when um when pink, it's pink in an alkali. That is by the addition of a base. Okay. And at the end point it goes colorless again. But at the end of the day, what we really need to achieve is that just that color change. Immediately we see that color change, we'll stop dropping in our base. Okay, we'll just stop the base dropping in. So in order to do calculations in practical titration volumetric analysis, you can see what titration means. Concentration of unknown solution being obtained from that of a known solution. Did I talk about qualitative and quantitative? Qualitative analysis have to do with identifying elements or compounds present in a particular sample, while quantitative is when we compute or calculate the amount or quantity of an element or a compound present in a given sample. So in quantitative, that's where we find this titration process. Okay, it's just like one having to do with identifying which and which element, the other one has to do with numbers, calculations. Okay, so quantitative analysis, we see volumetric, which is what this titration is under. Okay, then um, so these are the formulas we need to know, have at the front, back, center of our minds when we do volumetric analysis. From formula for molar concentration, okay, and also knowing the units of these things, knowing the number of mole. There are three formulas, key formulas that can help us determine number of mole, whether it be in this topic or away from this topic. One key formula is that number of mole is equals to mass divided by molar mass. Also, number of mole is equals to concentration times volume. Also, number of mole. Oh, it's everything that is actually written here. This is it. No need for me to rewrite it. Okay, number of mole is also um number of molecules, capital N, in terms of Avogadros, divided by 6.02 times 10 raised to the power 23. So these are the formulas we can use. Now, when they say number of moles is concentration times volume divided by 1000, that is when your volume, you don't have to divide by 1000. You divide by 1000 when your volume is not in liters. If your volume is in liters, you don't have to liters or decimeter. You don't have to divide by. But if your volume is in centimeters cube, decimeters cube rather. If your volume is in centimeters cube, then you now use this formula. Okay, you now use the formula of concentration times volume divided by 1000. But if your volume is measured in liters or decimeters, you don't have to divide by 1000. I hope you all understand. So that is to find mole, number of mole. Then another thing we may be required to calculate is mass concentration. Very easy. Mass concentration have to do with molar concentration, or rather concentration in mole per dm cube times molar mass. Okay, so always know this is mass concentration. I hope you people are jotting down. If you want me to repeat something, you let me know. If you are not understanding something, you tell me to say it again. So we say mass concentration. I saw a question on this in, I think, 2024 or 2025 past question recently. Mass concentration. Okay, you know mass is in grams, right? So mass concentration is mass per dm is equals to molar concentration time, which is in mole per dm cube, is the unit. Always remember your units. Okay, times um, molar mass. So sometimes in a single question, you may be needing to use both this formula, this second formula, then this last formula. You might be using multiple formulas to solve only one question, because they are linking to each other somehow. Then for standard solution in titration, we can't do a titration solving without really needing this formula you can see here in asterisk. Our CAVAB, CBVB. Ca is concentration of acid, Va concentration of volume of acid, Na number of mole of acid, Cb everything is written here in fact. Okay, then mole ratio is acid over base. So that's the basics. Now look at this question. The mass of anhydrous sodium, okay, of anhydrous sodium tetra also sulfate 6 present in, like I said, I'm repeating, the essence of all those titration is to know unknown concentration and to know that you first find the volume. So since titration is a volumetric analysis, it helps you to know the volume of acid. It is by that experiment, then when you know that volume of acid, then you will now be able to easily calculate your concentration in the question they will give you in your exam, and to be able to calculate any other thing. Back to the question on the screen. It says the mass of anhydrous sodium tetraoxosulfate 6 present in 500 centimeters cube of 0.5 mole, okay, molar, the number of sodium tetraoxosulfate particles present in the, so, oh, okay, we are calculating the mass first of all. Now, when we see questions like this, first thing that will come to your mind, what is the formula for mass? How do we calculate mass in volumetric analysis? Then you would come and remember the formula that number of mole is equals to mass over molar mass, which means that mass will now be equals to number of mole times molar mass. So now you have to figure out what the number of mole is and what the molar mass is. Okay, now the number of mole is not given us in the question. Okay, number of mole is not given to us in the question. So we have to look for our number of mole. So how do we look for our number of mole? We are going to use that CV formula. Now, this 0.5 molar stands as our concentration. Okay, you can see here that remember I said number of moles is equals to CV, concentration times volume. Now in this case, our volume is in centimeters cube. That's why we are now saying it's over 1000. If it is in liter or decimeter, you don't have to use 1000. I'm emphasizing that again. But I presume, or I think your concentration, your volume is usually given to you in liters in your exams, but just so that you don't get caught unaware, take note of it, so that you will be given something that is in decimeters cube and you will keep solving with the same formula. So the reason for that conversion, because 1 liter is equals to 1000 centimeters cube, so we have to convert. So back to this. So when we do that, since our mole is 0.5 and our volume is 500, we divide it by 1000, cancel this, cancel this. So it's now 0.5 times 5 divided by 10. And then we'll get a number of mole to be equal to 0.25. Since we've got a number of mole, we can now go and find the mass that the question actually asked us to find. Remember, I told you earlier that sometimes you might be solving one thing, but you end up using two different formulas to achieve that your one answer. So since we have got to number of mole, we can now fix back into this equation and get our mass to be, the answer we get 0.25 times molar mass. Molar mass are these things they usually give us in the bracket. Okay, molar mass of sodium is 23. That is for one sodium. This equation here, the problem is not dealing with only one sodium. You look at the formula. The formula is 2 sodiums, and so we'll have 2 times 23. And we have 1 sulfur in the formula plus 32. That is for the 1 sulfur. Plus we have 4 oxygen. So now say 4 times 16, because this 16 is for only 1 oxygen. So 4 oxygens would be 4 times 16. So everything, you multiply the ones that need to be multiplied and you then sum up. We'll get this. as our molar mass, gram per mole. Okay, so we'll get our molar mass, we'll fix it back into the equation and get our final answer. Now the next question, the B, says you should find the number of, so you can see that the molar mass that is in question B, we use that information to answer question A. So you have to look at your full question. This whole question is for only example one, so you have to look at the whole question so you will not be missing any detail. Okay. Now the number of sodium tetrasulfate particles present. Number of particles present. Then we will now go back to that Avogadro's formula. Okay. Number of particles. Where is the formula? This first formula. Okay. So that is to say we can rewrite this formula. We say number of moles is equals to number of particles divided by the Avogadro's constant. Okay. So this one is donated by capital N. It's different from small n. Small n is number of mole. This number of the molecule or particle or atom. It depends. Particles can be particle, and molecule, atoms. Okay, whatever. All these are what comprises particles. Different from number of mole. So if we're fixing into that formula we see earlier, we are going to be multiplying this time around. Okay. Please, if I'm not alone here, if you are understanding our explanation, please raise up your hand. I said raise up your hand. I want to see a thumbs up. If you don't understand so far, let me see your thumbs down. Winner doesn't understand. Winner, please unmute and tell me the parts you want us to go over again.
The first question. I need you
The,
to
the
explain the
first
first
question.
question again.
Is it this one? This one you can see on the screen. Is it the A? Ah? Winner.
Yes, yes, ma'am.
Okay. Now look at the question. They said the mass of anhydrous tetraoxosulfate present in 500 centimeters cube of 0.5 molar. Now look at it. They said we should calculate the mass. That is, let us bring out all the variables. Mass we don't know. Okay. And then what else again did they give us to be able to get this mass that we don't know? They gave us volume. How do we know that they gave us volume? We see 500 centimeters cube. This is the unit for volume. So we have 500. Now what else did they give us? This is concentration. Okay. This is what is going to be representing our concentration because the amount. This capital M is molar and tells us the amount of a substance. So in some other questions, you see concentration written as mole per dm cube. Okay, when we see this, we'll know they're also talking about concentration. So it's also amount. Now, our concentration, which is denoted by C, is given to be 0.5. So these are the only two things that they gave us to be able to find our mass. Then the next thing we'll ask, what formula are we going to use to find mass? the formula for mass that we would use. We know the general formula that number of mole is equals to mass divided by molar mass. We know that. So we can now derive the formula for mass from here. When we cross multiply, we now have our mass equals to number of mole times molar mass. So that is to say, for us to know what mass is, we need to know what number of mole is, and we need to know what molar mass is. Now, what is number of mole? It wasn't given to us in the question. We're only given V and C. But then we should also remember that there's another formula where number of mole is equals to C times V. At least we can now use this V and C. The reason why it's given to us there is for us to find our number of moles so that we can find our mass. So our number of mole is equals to V or C times V or V times C times V. These are our number of mole. Now, so therefore, we fix it into the equation. C is what? We said C is 0.5. And our V is what? V is 500 divided by 1000. Why are we dividing by 1000? I said because our volume is in centimeters cube. Anytime we are doing calculations of volumetric analysis and our volume is in centimeters cube, we have to make our formula to be C times V divided by 1000. But if our volume is in liters cube, sorry, what is liters cube? If our volume is in liters or decimeters cube, we don't have to use that 1000 at the bottom. Our formula will just be C times V. Finish. But we are dividing by 1000 because this centimeters cube is a smaller unit. So we need to divide by 1000 so that it will be um it could be in the equivalent unit for volume that we need. Winners, do you understand up to this point? Okay, I can see your thumbs up. So from here, we'll now find our n. When we calculate this 0.5 times 500 divided by 1000, we'll get, when you use your calculator to punch everything together, you get 0.25 moles. Now we have gotten moles. Let us not get distracted, even though we are passing through different equals to get our mass. Remember, it's mass that they asked us to get. Okay, so don't get confused or distracted. Our aim is to get mass, but now we've gotten number of moles. Let's go back to getting mass. Remember, for us to get mass, we need number of moles and molar mass. We've got a number of moles. Now we need to get molar mass. How do we get molar mass? Molar mass is gotten from these numbers we see in brackets. These are molar mass, okay? So they gave us the mass of each element. The molar mass now of each element. Of sodium, of sulfur, and of oxygen. It's this sodium, sulfur, and oxygen that makes up our sodium tetraoxosulfate 6. Now I say in sodium tetraoxosulfate 6, which is the compound we are dealing with in 1A, the compound is not just one sodium, it's not just one sulfur and one oxygen that is inside. Okay, we have two sodiums inside. That is why we are saying Na2. It means there are two sodiums. We have one sulfur inside. That's why you see sulfur is standing on its own. There's no subscripts near it. No 2 at the bottom attached to it, or 3, or any number. Now, and then we have 4 oxygen. You see, the subscript of 4 is close to oxygen. So that is why, since the molar mass of sodium is 23, and then in the formula, the molecular formula, this, we are seeing 2 sodium. We now say 23 times 2. Our sulfur is just 1. The molar mass is 32. That is just 32. We're not multiplying by anything. or maybe you want to multiply by 1, it's still 32. Now, for our oxygen, we have 4 oxygen in the formula. So since one oxygen is 16 molar mass, 4 oxygens will be 4 times 60. So when you multiply and add everything together, we'll get our molar mass to be what? 142 gram per mole. So now we have found our moles, number of moles to be 0.5, and our molar mass to be 142. So finally, we can get what our mass is. So now we are going back to our origin. The treasure we're actually seeking for from the beginning. So then our mass, now we'll fix it into our equation for mass. It's equation 1. Okay. So um our mass will now be 0.25 times 142. We now understood? Hmm? All right.
Yeah.
Then it okay. So the next question is on number of particles. That one we know that when we see anything number of particles, we know we are using Avogadro's formula, which is number of moles equals to number of particles. Particles can be molecule, atom, whatever. Number of particles divided by Avogadro's constant. So we can go on and on. You see, in this case, we use just CV, number of mole divided by volume. Why? Because our volume here is in decimeters cube. Are you seeing it? We didn't divide anything by 1000. Okay? We now you're thinking.
No, I mean that's true.
You what? Yeah, what?
It's
You mean
true.
what? Yes, it's true. So you see our volume is in decimeters cube, not in centimeters cube. That is why we are not dividing by 1000 again. So be careful when you are using your formulas. So we don't just blindly follow a formula. Now, yeah, sometimes when we see things like STP, standard temperature and pressure, okay, where we get molar volume, the molar volume value, the value for molar volume is constant. Is this 22.4? It wouldn't change. It's a constant volume now for 1 mole. Now they said calculate the volume of hydrogen chloride gas at STP. That is, when you see that at STP, if volume is involved, you know that even though they don't write it there, you make use of this 22.4 dm cube. Would yield 1.6 dm cube of 0.15. So we have seen 1.6 dm cube. That is, we have been given a volume there. 1.6. 0.15 m. That's our concentration. 0.15 of HCl. What are we calculating? The volume of hydrogen chloride gas. Volume of hydrogen chloride gas. When molar volume is equal to 22.4. Okay. So we know that number of mole is equal to what? Concentration times volume. And also we know that 1 mole is giving us 22.4 dm cube. Okay. Now when we get our number of moles from here, remember, if you read this question very well, don't get confused. We are dealing with hydrogen chloride gas and hydrogen chloride solution. HCl aqueous. They are two different things in two different they are in two different states. One is gas, the other one is a solution. Okay, so the first one is what's going to yield the second one. That means one of them is in the reactant, the other is in the product. What is going to be formed? Okay, so trying to open my calculator. By the time we multiply 0.15 by 1.6, okay, we have 1.6. We have 0.24. Okay, that is the number of mole for our aqueous HCl, for HCl aqueous. Okay, is this 0.15 times 1.6, which is was 0.24. And remember, based on the equation, they said what it is the HCl gas that will give us our HCl aqueous that will form our ACM. So let's assume it to be like this. Okay, now since we have gotten the number of mole for the aqueous HCl to be 0.24, okay, we are now looking for the volume of uh the HCl gas, and then we know that volume of gas at STP, remember this is specifically for gas, volume of gas at STP is 22.4. Okay, and then this volume of gas, it is what we relate to be equivalent to 1 mole. Okay, so if 1 mole is giving us this volume of gas at STP, that's the basics, the what we're going to use to solve what we actually need. Okay, if 1 mole is giving us this at this volume, okay, then this 0.24 mole will give us how many volume? That is what we want to know. So here we can cross multiply, and when we cross multiply, we have the unknown volume, okay, is equals to 0.24 times 22.4. So which is going to give us, okay, no need to calculate, 5.38. Okay, so when we see questions like this, we should first identify the essence of the molar volume. The essence of the molar volume at STP is to tell us that the what volume is equivalent to 1 mole, and to relate it to get the unknown volume. So first off, we'll find our mole from the value of our C and V given to us. Okay, and then to know the volume, the unknown volume is to relate the ratio of volume and mole. Since 22.4 volume gives us 1 mole, how many volume will now give us 0.24 moles that we just calculated? Okay, so let us see actual WAEC examination questions. I hope so far you people understand. If you don't understand, please identify. Can you all see my screen clearly? Okay. So now, someone said they can't see my screen. Golden can see my screen. The rest of you, can you see my screen? Christine can. Oh, Melody cannot. Winner can see my screen. I presume it's your network. For those that cannot see, just keep refreshing, or you can exit the class and join back immediately. Because me too, I can see my own screen. So we have some few more minutes left. Now this first question says, in an experiment, 20.0 centimeters cube, that is telling us volume, of a solution containing 4 gram per dm cube. What unit is that? What is that 4 gram per dm cube telling us? Someone should tell us. Is the unit for what?
The units for hello.
Sorry, I can't hear you clearly. Hello? Yes, I'm waiting. What is that
Is the
4
unit
gram
for
mass what? Sorry. Mass concentration. This is telling us our volume. This is telling us our mass concentration. Also, the hydroxide was neutralized. So we can see this is a titration process. Okay. By another volume of dilute tetraoxosulfate. So the first question is, write a balanced equation for this reaction.
mass
So you people should write.
concentration?
Yes, winner. Mass concentration. Write a balanced equation for this reaction. What will be the balanced equation? If you read the question, you know the two things we are dealing with. Sodium hydroxide and H2SO4. This is 2023. Last question. All of you should write it on your notebook. The balanced equation between sodium hydroxide and tetraoxosulfate 6. Tetraoxosulfate 6 is H2SO4. And anytime you see neutralization reaction like this involving an acid and a base, the product you will get is a salt and a water. Okay, so salt making up a positive and negative ion, a molecule that an ionic compound, a compound that is made of positive and negative ion. That's the salt that will be formed, and also the water, H2O. So I basically told you what to write, but what you need to do now is to balance your equation. So all of you should write it on your notebook and tell me what is the balanced equation. I'm giving 2 minutes for this. Write the equation on your notebook and balance it. Then tell me what you got. Okay, time's up. Tell me your balanced equation. What should I write? Tell me as you're saying it, I'm writing it on the screen. Who is going first? Okay, I can see Melody's response on the screen, on the chart. Very good, excellent. So this is what Melody got. 2 sodium hydroxide plus, Melody, I hope you derived this yourself. You didn't go to copy from anywhere. Melody,
No, ma. Yes, ma.
very good. So this is the balanced equation. All right, sodium in reactant is the same as product, OH the same, hydrogen, so and so on. Now the next question says calculate the concentration of the acid in mole per dm cube. Okay, now let's not get confused by the units. So first things first, what is concentration? How do we calculate for concentration? Concentration will be number of mole divided by volume. So if we're looking for concentration of acid, is number of mole of acid divided by volume of acid. Do we know the number of mole of acid? Someone should tell me. What is the number of mole of acid? Okay, I'm asking, is it in the question? The number of mole of acid, is it in the question?
No, ma.
Good. So that means we have to calculate for it. But now, the VA, volume of acid, is it in the question? Mm?
Yes, ma'am.
Good. So what is the volume of the acid?
20 centimeters cubed.
No, the acid.
8.7 centimeter
8.
cube.
Very good. 8 is look at it, it's written here. 8 centimeters cube of dilute tetrahydrosulfasis acid. Okay. So we need to know the number of mole of the acid so that we'll be able to calculate the um so that we'll be able to calculate the concentration of the acid. So how do we calculate that? We say number of mole is equals to mass divided by molar mass. Were we giving mass? We're giving mass concentration. Okay, mass concentration to be 4. And our molar mass, what is our molar mass? We're dealing with the acid. The acid is H2SO4. It's easy to find the molar mass. You see, in this actual exam question, it was not given to you, but it's something you can know. So I leave it to you. You people should tell me what the molar mass is. Calculate it and tell me. No, actually, this 4 is a mass of base, not of acid. So we also don't know the mass of the acid. So that means we have to find the mole. We have to find the concentration of the acid first, so that we'll know we have to find the mole of the base for us to be able to find that of the acid. So you can see how this thing can end up looking tricky. Remember, all this is to find the number of mole of the acid. But to get number of mole, we need mass over molar mass. But we're not given the mass of the acid. We can only get the molar mass. So that means we will now find the number of mole of the base first so that we can get that of the acid. Okay, of the base, the number of mole is 4. I'm sorry, the mass is 4, given here. Mass concentration is what we're going to use. Divided by our molar mass for base, sodium hydroxide. Sodium is 23, oxygen is 16, hydrogen is 1. That is giving us 40. So divided by 40, our number of mole for base is 0.1 mole per dm cube. Okay. Now we've gotten that for base. We need to get that of the acid. How do we do that? Remember, we wrote a balanced equation. That was not for fancy. We would use it to answer this II question. Okay. So remember, in our balanced equation, we wrote 2 sodium hydroxide will react with H2SO4 to give us our salt plus water. Okay, so you see here that it means that we require 2 sodium hydroxide for every 1 mole of acid. So the reaction is a 2:1. So if 2 moles of sodium hydroxide give us 1 amount of acid, if it's a 2 ratio 1, then this sodium hydroxide that we just calculated to be 0.1. We'll put it beneath here for the sodium hydroxide side. Will give us how many moles for our acid. What we can do here is to cross multiply. And when we do that, 0.1 times 1 and then 2 times the unknown. 2 times the unknown is 2 unknown, which is 2 number of mole, is equal to 0.1 times 1. That is also going to give us the same 0.1. So divided by 2, divided by 2, that means it will now be 0.1 divided by 2, which is 0.05. So we have finally gotten the number of mole. Okay, we've gotten the number of mole of the acid to be what? 0.05. Now this 0.05, it gives us the 0.05, it's measured in a mole. We see this 0.1 mole per dm cube, and this is also a mole. Okay, and then but our volume of acid, they said our concentration should be in mole per dm cube, and we can see our volume in the equation is in centimeters cube, so there's a contradiction here. So we have to make our volume to be in mole per dm, to be in dm cube. Okay, so we have to convert the centimeters cube to decimeters cube. How can we do that? By dividing 8 by 1000. So our volume of acid, we know it to be 8, but 8 divided by 1000 is 0.008. Who is confused up to this point? Who does not understand? So at the end of the day, we should be focused of our formula being used and what exactly we are looking to solve for. And also we should be mindful of our unit. Okay, especially that of volume. It's going to ruin certain things for us, but it's good to be mindful of it. Okay, so the first thing is to what? Look for the number of mole of the base. From there we can know that of the acid. Okay, and if you notice, this is in mole per dm cube. It has to be in mole. Okay, so we have to eliminate this dm cube, and how we can do that is by relating it to our volume of centimeters cube. So we are going to say, since we get our molar concentration to be 0.1 mole per dm cube, okay, we have to make it in mole. And so to do that, we're going to be multiplying it by our volume of our base, which is 0.02. Why is it 0.02? Because our volume is in centimeters cube. We have to divide by 1000. So we'll multiply these two together. we get 0.002. So this is actually going to be our mole for our base. And so when we relate the equation here, this is supposed to be 0.002, please. And when we cross multiply, we'll have 0.002 divided by the 2. Okay, and that will give us, so the reason why we are going to and fro like this is because of the units. That's why I said you have to be mindful of it. This divided by 2. So rather than 0.01, we get 0.0, rather than 0.05, we get 0.001. Okay, so this is finally our number of mole of acid. We'll fix it back into the concentration problem. So when we divide these two, we would get equal to 0.125. Please, if you have questions, you can ask. Do you have a question? Hello?
No, ma.
Golden. Who else is here? Oh, I'm the only one with. Okay. Golden. Obawumi. Winner.
Ma, can you read?
Yeah. All right. Okay. Now, questions like this, when we are dealing with
Um,
neutralization process,
from
we should,
where
yeah, from where? I really can't hear you. Winner, what are you saying? From where? Hello, Winner, can you hear me? Winner,
I said from where you said that our balance equation is not for fast. Start for there.
from the balance equation. Okay, you know that for this kind of question, we need to have a balanced equation. So our balanced equation was sodium hydroxide was 2 sodium hydroxide plus H2SO4 to give us our salts, sodium 2SO4 plus H2O, 2H2O. These are our balanced equation. This equation, the main purpose of it is to tell us the ratio of sodium hydroxide and tetraoxosulfate 6 that is involved in this process. Where you will look at the coefficient, the number at the front of each of the element. Okay, this one, the coefficient is this 2, and for the H2SO4 the coefficient is 1, so it's not written. So that means it's a 2 ratio 1 something. Now, our question says we should calculate the concentration of the acid, and we know that concentration is equals to number of mole of acid is over volume of acid. Okay, based on this N equals to CV formula. Now, what is the number of mole of acid? Number of mole of acid is equals to mass divided by molar mass. We can derive the molar mass of acid by counting the mass of hydrogen, sulfur, and oxygen. But then we're not given the mass of acid. This 4 gram per dm cube, it's not mass per se, it's mass concentration. And also it's not for um, acid, it's for H2SO4. So how exactly are we going to find this since we have two unknowns? We have unknown in number of mole and unknown in mass. We can't find the number of mole from only molar mass. So what are we going to do? We're going to now first look for the number of mole of our base. So we are now leaving again this formula to look for number of mole of base. Okay, that is number of molar concentration of base rather, because this our mass given here is mass concentration, so it's molar concentration we can find with this mass concentration of 4. So molar concentration, which is we can write as N, is equal to mass concentration 4 divided by the molar mass. Molar mass of sodium hydroxide is 40 because sodium is 23, oxygen is 16, hydrogen is 1, which is 40. Now 4 divided by 40 is 0.1 mole per dm cube. Okay, now this is molar concentration. We need to find number of mole, not molar concentration. So what are we going to do from here? From here, to get the number of moles, since we have gotten the molar concentration, the difference between this number of mole and molar concentration is this dm cube that is here. So to make this molar concentration to become number of mole, we're going to multiply by the volume. Remember, this is of sodium hydroxide. So we multiply by the volume of sodium hydroxide. So that is to say 0.1 times, look at it, 0.1 mole per dm cube times the volume of sodium hydroxide. It is 20 centimeters cube. We have to convert it to decimeters cube because we are dealing with decimeters cube. You see, they say our answer should be in decimeters cube. So we have to convert. And we'll convert 20 centimeters cube to decimeters cube by dividing it by 1000. And when we divide it, we'll get what? We'll get times 0.02 decimeters cube. Now this decimeters cube units, we cancel out this 0.1 with times 0.02 to give us equal to, this will give us equal to 0.002 mole. Now our unit is now in mole. Remember, this is for sodium hydroxide. We have not found for the acids that they asked us to find for. But since we get that of sodium hydroxide, we can now get that of the acid. How? Is by going back to our balanced equation. From our balanced equation, we said every 2 mole of sodium hydroxide is equivalent, or we will require 1 mole of H2SO4. So it's a 2:1 something. So since we get the number of mole of sodium hydroxide to be 0.002, that is to say, what we are doing here in essence is that we are comparing the number of mole to the coefficient of the balanced equation so that we'll get the unknown number of moles. Again, I repeat, what we are doing here is we are comparing the coefficient of the balanced equation with the number of moles so that we'll get the unknown number of mole. So this is the unknown number of mole, that of the acid. This is another way of getting the number of mole without going straight to these equations. So from here, if 2 will give us 1, then 0.02 will give us how many? That's in what this is asking. So it will now be 2. 2 times the unknown is 2 unknown, which is the unknown is number of mole, equals to 0.002. So we divide both sides by 2. So 0.02 divided by 2 will give us equal to 0.001 mole. Now, this is our number of moles for acid. Finally, we have got to Na. So concentration is equal to number of mole of acid, which is 0 what? 0.001 divided by volume of acid. Volume of acid is in the question, but it is in 8 centimeters cube. We don't want centimeters cube because they said our answer should be in mole per dm cube. Remember, this is what? Mole. So we have to convert our 8 centimeters cube to mole per to decimeters cube. So to do that, it is simply 8 divided by 8,000. So this will give us 0.008 decimeters cube. Now when we divide this 0.001 divided by 0.008, it will give us what? 0.125. Okay. Now this is the units, mole from the number of mole, and dm cube from the volume. Now you see, indeed it is mole per dm cube unit. Okay, time is exhausted already. Mina, I truly hope you understand. If you don't, you can actually go back to the videos again. When it's been uploaded in the platform, you can go and watch it all over again and carefully look at the steps. Okay. Winner, can you hear me?
Yes, ma'am.
All right. Okay. Thank you for coming to class today, every one of you. I hope you all learned something today. I want to hear from everybody. I hope you all learned something today. Winner.
Yes, ma'am.
Yes, ma'am.
All right. Golden. Winner. Okay. He also learned something today. All right. That's all for today. Bye bye.